with the derivation of the Nernst equation. Yes?
I feel like in the equation, finding the n value is difficult.
Have you done some?
Yeah, one of the questions, like I was just confused with how to find it. So.
Do you know how you have an oxidation half reaction, a reduction half reaction, and you have to add them together to get the overall balanced equation? The number of electrons that you have to balance out, that cancel, that's the n value. Now, when we did this example yesterday, something like this, I mean, the electrons aren't shown. How do you know how many electrons, what the n value is? Well, we'd have to balance this thing. We'd have to break up into this to this being the oxidation half, this going to that's the reduction half reaction, and then come up with the number of electrons from that. And when you add those two back together, the number of electrons that you have on each side canceling out, that's your n value. It's not bad. That part is not bad. What example did we do? I had lots of people were confused yesterday. Oh, this was the one, right? And it was not very obvious how many electrons were being transferred. Usually, you're going to have the two half reactions. You have to split them up and balance them out. And when you put them back together, it's not bad. You have to do a couple of them, and you're going to feel perfectly fine. In fact, we'll do an example of it, two of them. So I want to remind you, we use the Nernst equation to find out what the cell potential is if we're not at standard conditions. The table, oh, and by the way, I have a table to give you. I finally remembered to make some copies of it, so you don't have to have the clumsy book.
Yeah, Michael. Were you able to remove my name for that blood thing?
It's a good book.
Oh, you have to do it. I can't.
Yeah, okay.
So like, I'm not the one anymore. So like, trying to find the people who are the wandering around with like.
Just the malaria.
Okay.
The first example I'd like to go through kind of with you, but at first, now that I've shown it up here, I want you to just look at it and ponder it and see if you can make sense of what they're asking for. You want to know what the cell potential is, but see what you're given, and would you be able to do this? Would you be able to write the chemical equation for the reaction? If you're given the line notation? No? I think we can do that. You know, this is the anode and that's the cathode. What are the two reactants in the reaction? Zn by itself? Plus what? The Zn has to be a positive too? No. Those are the two reactants. In the anode, this is changing into this, so that's a reactant, that's a product. And in the cathode, that's changing into this, so that's a reactant, that's a product. That's the way we read that line notation.
Oh, that's okay.
Yeah, yeah. So this is what we're starting with, just in the anode compartment, and this is the starting material in the cathode compartment. So those are the two reactants.
That makes sense.
And then we get zinc ion and copper metal. There's our chemical equation. So up here it says that we're starting with zinc, the zinc ion having a 1 molar concentration, and the copper ion to begin with having a 1 molar concentration. Calculate the cell potential. Now at the beginning we had standard conditions. This was standard, but they never asked us what the standard cell potential was. It says, what is the cell potential after the reaction has operated long enough for the zinc concentration, that's that, to have changed by 0.2 moles per liter. If this changes by 0.2 moles per liter, they didn't tell us whether it goes up or down. Do you know?
It goes up.
Is there a way that we know?
Leo is Leo. So it goes up.
That's right. That's right. Now, see this arrow right here? How many ways does that go? It goes one way. Remember, galvanic cells are always for spontaneous reactions. It's going to spontaneously go that way. That's the way galvanic cells work. So we know that the reactants are going to go down and the products are going to go up as the reaction proceeds. So it's operated long enough for this to have changed by 0.2. So it goes from 1 to 1.2. What about the copper then? Copper ion. It goes down by 0.2 because it's a 1-to-1 ratio. Like that. So now we know where we're at in the reaction, what the ratio of products to reactants are. So we can go ahead and use the, now we're not in standard conditions, that's where we have to use the Nernst equation. Nernst equation looks like this. Cell potential equals the standard cell potential for the table values minus 0.0591 over N times the log of Q. Anybody have the standard cell potential?
Yeah, 1.1.
It's 1.10. How'd you get that, Saloni? Yep, the reduction of copper is 0.34. The oxidation of zinc, 0.76.
Yeah.
Ah, you're looks like you got papers falling. Oh, not 0.74, sorry. 0.76. So those two added together gives us the 1.1 volts. By the way, this was found on the table as a reduction, so it had to be turned around. It was negative 0.76 as a reduction. That's how we get the positive 0.76, because now it's oxidation. Okay? So the standard, this number right here is 1.1 volts minus 0.0591 over, what's the N value this time? 2. Oh. But you can, it's pretty obvious what's happening here. We got zinc changing to zinc positive 2 is giving off 2 electrons. Copper 2 is changing to copper that's taking in 2 electrons. So N value is 2. And then the log of Q. Q is products over reactant concentration. Ignoring the solids, it's 1.2 over 0.8. The answer you get is pretty underwhelming. Even though you would think, oh, we've changed by 0.2 from 1, that's like a 20% change in the concentrations. However, what winds up being the change in the voltage? What is the new cell potential? It's 1.09. Is that what you said, or 5?
What? I got. You subtract 0.0052. I got.
0.0052. Yeah, so you're going to get 1.095 or 94 or something, right? So the new cell potential is 1.09 volts. So in standard conditions, it was 1.1. Now that it's about 20% done, it has gone down by a 100th of a volt. So you're not going to notice a big change in the voltage until that fraction starts to get bigger and bigger. Yeah.
So for the battery lab, should we try to like measure the voltage like ASAP?
Yes, because as you run your electrons through your current, the voltage is going to be going down. You'll see that. You'll see it happening.
Oh, okay.
Anything else about this problem? I'm going to ask you to try one now. We have an electrochemical cell, also known as a galvanic cell, consisting of a standard hydrogen electrode and a copper metal electrode. So those are the two compartments, when you have a hydrogen, when you have a copper. What is the cell potential at 25 degrees if the copper electrode is placed in a solution in which copper ion is dead? I'd like you to try this problem, but before you do, I think we should talk about this expression right there. A standard hydrogen electrode. What do you think they mean by that?
Or like 2H++, 2.
Yeah, that's going to be that baseline standard reduction. That's the, and again, this is found about a third of the way down in the right column of the table. 2 hydrogen ions gaining electrons, making H2. And the reduction potential is 0. That's what they mean by a standard hydrogen. You can't use a bar of hydrogen in the actual electrode. You'd have to have platinum or graphite or whatever. But so one of your compartments has this reaction going on. That's what they mean by it. And you know enough to do. I'm going to leave you a few minutes, see if you can try to do this on your own. And don't hesitate to talk to somebody and see if you can walk through this thing. The number of electrons that are transferred. You know how we have the 2-half reaction? You have to get the number of electrons equal before you can add the 2 together. That number of electrons. What's that? Yeah. It gives you the hint right there. The metal electrode is going to be neutral copper. And, well, yeah, you're going to have to look that up in the reduction potential table. The one of them you have to turn around.
What is this standard hydrogen electrode? Does that mean they're all 1 millimeter?
Yes. Yeah. And the gas is 1 atmosphere.
Just want to look at this. How do we know which ones are reducing and the oxidation?
You have to figure out which one does which. It's not telling you, is it? But you can determine it. This is one of our half reactions. The other half reaction is the reduction of copper ion to copper metal. Now, how do we know that? It says we have a copper metal electrode, and it's placed into a solution of copper. So the reduction potential is 0.34 volts. It doesn't tell you which one oxidizes, which one reduces, but what's up there, and you should be able to figure it out. Yes?
You have to add them together and be positive.
Right.
So
That's what it is.
It has to be, no, yeah, it has to be oxidizing and that's being reduced.
Yep. Oh, that was pretty cool. Yeah. 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 So, these are both written as reductions. One is going to have to be turned around to be an oxidation. When you turn one of them around, when you add the two potentials together, it's got to be a positive number. If I turn this one around, it's gonna make it negative 0.34, but negative 0.34 added to 0 is gonna be a negative